This video series contains recorded tutoring sessions covering the topic of thermodynamics from the perspective of a general chemistry course. There's a table of contents for each video in the video description box, and there's a table of contents for this particular video in the progress bar. Here are some YouTube controls which you may find useful while you're watching the videos. So the next chapter is dealing with thermodynamics concepts. Let's start working on that. So the first thing that we need to understand is it's very important to understand the difference in this chapter between a level and a change. Don't confuse levels and changes. So let's think about the symbols x and delta x. So which of these symbols stands for the level of x? And which of these symbols stands for the change in x? Can you tell me?
The change in x would be the delta x. And the level would just be regular x.
That's right. All right, so this might seem like a boring distinction, but this is important in Chapter 7. We need to work hard not to confuse levels with changes. So whenever we're working on this chapter, try to make an effort to specify whether you're dealing with a level or a change. So let me give you an example of what I mean by that. Here are some values for x. So these are some values for x. Are these levels or changes?
Levels.
Because they're x's. Now, what would be the delta x as we go from here to here?
5.
Good. Positive 5 or negative 5?
Positive 5.
Okay, so let's keep going. What would be the next delta x?
Positive 1.
Okay, let's keep going. What's the next delta x?
Positive 2.
Okay, how about this one?
Negative 3.
Good. And let's do this one.
Negative 6.
Good. Are these levels or changes?
Those are changes.
That's right. So hopefully this makes clearer the distinction between levels and changes. Now, what would you say about the levels in this region? Let's look at this region compared to this region. Would you say these levels in this region are increasing or decreasing?
Those are increasing.
Good. So who is increasing? X is increasing here. The levels are increasing. Now, what would you say about the changes in that region? Are these changes positive or negative?
Those are negative. Those are positive.
That's right. These are positive changes. Okay, so how would you analyze this region? What would you say about the levels here?
Those are decreasing.
X is decreasing. And in that region, what would you say about the changes?
Those are negative.
Yep, that's right. They're definitely negative. Okay, so do you see what are the lessons we can learn from this? So when the level is increasing, what does that tell you about the changes?
The changes are positive.
That's right. When the level is increasing, the changes are positive. What would be the wrong thing to say? If the level is increasing, does that mean the changes have to be increasing? When the level is increasing, does that mean the changes have to be increasing? You can see that's not right, right? These changes are not increasing. So that's the point I'm trying to make. Just because the level is increasing doesn't mean the changes are increasing. You don't want to say that. If the level is increasing, that doesn't mean the changes are increasing. These changes are not increasing. Instead, when the level is increasing, the changes are positive. So how about when the level is decreasing? When the level is decreasing, what can you say about the changes?
The changes are negative.
Good. How about in the opposite direction? If someone tells you that the changes are positive, what could you say about the levels?
The levels are increasing.
Increasing. The levels are increasing. If someone tells you that the changes are negative, what could you say about the levels?
The levels are decreasing.
Good. Do you see the wrong thing? If the changes are negative, does that mean the levels are negative? No. Just because the changes are negative doesn't mean the levels are negative. You don't want to confuse the levels and the changes. Okay, so make an effort to not confuse levels and changes. That means don't confuse x with delta x. So let's do a little bit more work on this. If the level is increasing, what else could you say? If the level is increasing, what could you figure out from that?
The delta x is positive.
Great. All right, how about if the change is negative? What can you figure out from that?
The levels are decreasing.
Okay, what about if the delta x is positive?
The levels are increasing.
Okay, and what about if x is decreasing?
The change is negative.
The change is negative. Okay, so like I said, as we're going through this, try to be careful when you're talking. Remember, we want to avoid using the word it. Don't say it is increasing, or it is decreasing, or it is positive, or it is negative. Instead, say something like the level is increasing, or the change is negative. That'll be important in this chapter. Now let's move on to the next topic. Okay, so one of the key topics in this chapter is entropy. You should remember hearing your professor talking about that in class. That's kind of a difficult concept. Do you have any memory of this concept from class? How would you define entropy? What does entropy measure?
It measures like randomness of like a system.
Great. That was a great answer. Good. That was a good answer. Actually, entropy is such a complicated concept that we have to give a couple of different definitions. You can think of entropy as a measure of energy randomization. That's pretty close to your answer. Or energy dispersal. In general, entropy is a measure of the disorder of the system. So notice when things become more random, entropy goes up. Also, when things become more dispersed, entropy tends to go up. When things become more disordered, that's a synonym for randomization, so again, entropy would go up. Let's talk about the symbol for entropy. Do you remember from class? Have you picked up from class what the symbol is for entropy?
Would it be capital S?
Good, that's good. You might think it would be E, but it's not E. It's capital S. That's right. Capital S stands for entropy. Good. So let's say that things become more disorderly. If things become more disorderly, what would you say is happening to S?
It's increasing.
Good. More disorderly means an increase in entropy. What would you say is happening to delta S? Or what would you predict about delta S when things become more disorderly?
It would be positive.
Positive. Great. So this is the distinction I was making between a level and a change. When things become more disorderly, that doesn't mean that delta S is increasing. It means that delta S is positive. It's S that's increasing. So let's do another example. Let's suppose that the molecules become more orderly. What would you predict in that case?
S is decreasing and the change of S is negative.
Good. So would you want to say that entropy is negative? No. Entropy is not negative. Entropy is decreasing. You could say that the change in entropy was negative. The change in entropy is negative, but you wouldn't want to say that the level of the entropy was negative. Okay, now remember the phases. Phases are things like solid, liquid, gas, and aqueous. So let's say we have a phase change from solid to liquid. What would you predict about entropy in this case? What's happening to entropy here?
It's becoming more disorderly.
Okay, so what would you predict about the entropy? So that molecules are becoming more disorderly. That's right, a liquid is more disorderly than a solid, because in a solid, all the molecules are stuck in place, and in a liquid, they can move around.
So S is increasing and the change of S is positive.
Great, that was a good answer. Okay, so let's try this example.
S would increase even more.
What was your thought process there?
Gas is more disorderly than liquid.
Great, that's right. A gas is more disorderly than liquid. In fact, the word gas comes from the word for chaos. The word gas comes from the word for chaos because it's more disorderly. Also, another way to think about it is that in a gas, the molecules are more dispersed, right? In a gas, the molecules are more dispersed. Remember that energy dispersal also increases entropy. When things become more randomized or more dispersed, there's an increase in entropy. So with in both those ways, S would be increasing. What would you predict here about delta S?
It would be positive.
Okay, so your answer was a good one. Your answer was a good one for that question. Most of the material in this video series consists of tutoring sessions recorded with a student. However, I'm also going to add a few additional notes recorded on my own. You should know that AQ stands for aqueous phase. What does aqueous phase mean? Aqueous phase means dissolved in water. Can you figure out this one? If we go from solid phase to aqueous phase, what would you predict?
S would increase.
What was your thinking there?
Since the solid is being dissolved in water or aqueous, that basically means it's gonna be liquid, and liquid is or aqueous is more disorderly.
Okay, that's pretty much correct. That's pretty much correct. I would say that's pretty much correct. It's becoming more liquid-like, I guess you could say. It's not really a liquid. Remember, aqueous means dissolved in the liquid. It's not really becoming a liquid, but it is becoming dissolved in a liquid. So in a solid, the ions are all stuck together in one place. But when they dissolve, the ions go floating off in different directions in the liquid. So they will be more disorderly and more dispersed. When something dissolves, it becomes more disorderly and more dispersed. So you were definitely on the right track with your logic. Your logic was on the correct track. All right, so that was a good answer. So what would you predict here about delta S?
It would be positive.
Okay, so what would you predict here?
Since it's becoming more orderly, S is decreasing, and the change of S would be negative.
Very good. That's good. How would you answer this question?
It would be option A.
Good. So the basic analysis here is that you're going from liquid to gas. And we know that that results in a positive change in entropy. Good. That was a good answer. How would you answer question 9?
Option D, freezing water.
Okay. So what phase did we start with? And what phase are we producing here?
We're starting with liquid and we're producing solid.
So your answer is correct. Your answer is correct. Going from liquid to solid would be a decrease in entropy. Good. That was a good answer. So notice that for these problems, it might be helpful to specifically write down the phase shift. Notice how I specifically wrote down the phase shift here to make sure that I was not making a careless mistake. Let me just point something else out to you here. Is this question talking about level, the level of entropy, or the change in entropy?
The level of entropy.
How about this problem? Was this about the level in entropy or the change?
Change.
Okay, so I just wanted to point out to you that you need to be comfortable with both approaches. They might, the problem might refer to a change in entropy, or it might refer to the level of entropy. And in either case, you need to be able to interpret that correctly. Okay, I think you're getting the idea of those, so let's move on to our next topic. So that was our introduction to the concept of entropy. Like I said, I think you were getting the idea there. So our next topic is the concept of enthalpy. Enthalpy. So your lecture notes define enthalpy as the sum of the internal energy of a system. The definition in the lecture notes is that enthalpy is the sum of the internal energy of a system. So how would you fill in this blank? Enthalpy is a type of what?
Internal energy.
Good. Or just to be more general, it's a type of energy. You can see from the definition that enthalpy is a type of energy. So can you guess or remember what would be appropriate units for enthalpy?
Joules.
That's right. I don't know whether you just remembered that, or perhaps you could figure it out if you happen to know that joules are the typical unit for energy. In general, we measure energy in joules, so it should make sense that enthalpy will be measured in joules because it's a type of energy. Now, actually, even though this is the most standard unit, it's not the only unit you're going to see in this chapter. Another unit you might see for energy is this unit. What does this unit stand for?
Kilojoules.
That's right. So you might see enthalpy measured in either joules or kilojoules. So you have to be careful about the unit that you're using for energy. Do you remember this concept from class? Do you remember what the symbol is? Do you remember what symbol your class is using for enthalpy?
H.
Great. H. Very good. Capital H. Now that might not seem very logical. Again, it might seem more logical to use E for enthalpy, but instead we're using H. I believe where this comes from is the concept of enthalpy is closely related to the concept of heat. The concept of enthalpy is closely related to the concept of heat. because heat is another type of energy. So that's probably where the capital H comes from in this symbol for enthalpy. Now, actually, we're not usually going to use this symbol. We're actually not going to use this symbol usually because we're usually not dealing with, so does this refer to the level of enthalpy or the change?
The level?
This symbol refers to the level of enthalpy. That's right. So we're usually not going to use this symbol because actually most of our formulas are going to deal with the change in enthalpy. So can you tell me what would be a good symbol for the change in enthalpy?
Delta H.
That's right, and that's the symbol we're usually going to use in this chapter, I think. We're going to use delta H a lot more than H, because we're usually going to be dealing with changes in enthalpy rather than levels of enthalpy. All right, now remember, what are the concepts that we've talked about so far? If you think about it, we've talked about two concepts. We've talked about enthalpy, and we've talked about entropy. Enthalpy and entropy, those words sound a little bit similar, so you want to be sure that you don't confuse those. Entropy and enthalpy are two different things. So next we want to ask, what's the relation between those? Let's see if we can find an equation that shows us the relation between those. So here's the equation. So here's an important equation that we're going to be using. What does this symbol stand for?
The change of entropy.
Good. To be more specific, in this case, it's the change in entropy of the system. This is the change in entropy of the system. What does this symbol stand for?
The change of enthalpy in the reaction.
That's right. This is the change of enthalpy in the reaction. Now, actually, the system is the same thing as the reaction. The system is actually the same thing as the reaction, so you could just as well write the equation like this. You could just as well write the equation like this. It would be basically the same equation because the system is the same thing as the reaction. So you could also write this as delta S for the reaction. I'm writing it like this because these are the terms that I think you'll probably see in the problems. You'll probably see it expressed in these terms in the problems, but this would be an equivalent equation. All right, and what do you think this symbol stands for?
Temperature.
That's right. What would be the units for this?
Kelvins.
That's right. What would be the units for this?
Joules.
Good. So can you tell me what are the units for entropy? What are the units for entropy?
Joules over Kelvin.
That's right. Did you notice we didn't talk about the units earlier? We didn't talk about the units for entropy earlier, but now we can figure out the units from this equation. From this equation, we can figure out that the units should be joules over kelvins. So let's actually write that down. The units for entropy are joules over kelvins. So that should be memorized, or you can figure it out from this formula. The units for entropy are joules over kelvins. You can figure that out from this formula. Now, can we find this formula on the formula sheet? I think before today's session, the professor gave you the formula sheet for the next exam. Okay, so notice this doesn't exactly match any of these formulas exactly, which is unfortunate. But this is the version of the formula that I would encourage you to use for problems. This is what I would encourage you to use for problems. These versions are not really as helpful for problems. That none of these are exactly like this. So basically, I guess I'm saying that you need to memorize this. You should memorize this formula because you won't find it on the formula sheet exactly. Don't rely on the formula sheet for this. memorize this formula. Don't rely on the formula sheet, because the formulas in the formula sheet are not really as helpful for solving problems. These are not as helpful. Obviously, these are correct. They're correct, but they're not as helpful for solving problems. So in fact, I'm going to erase these now. I'm going to erase them because they're not that helpful for solving problems. Instead, you should memorize this version of the formula. During the tutoring session, I gave the student advice that was appropriate for her particular chemistry class. So of course, while you are watching these videos, you should keep in mind that some of the advice in these videos may or may not be appropriate for your particular chemistry class. For example, for your chemistry class, it may be useful to keep these additional entropy formulas in mind. Okay, let's try this problem. How would you do this?
"54 kilojoules multiplied by 1,000 joules over 1 kilojoule." And then we can cross out the kilojoules and we get 54,000 joules.
Great. That's good work. That's good work on that unit conversion. That's good that that didn't give you trouble. Here's another problem. You want to convert 45 joules per Kelvin into kilojoules per Kelvin. How would you do this?
We can do 45 joules over 1 Kelvin. 45 joules over 1 Kelvin multiplied by 1 kilojoule over 1,000 joules. And then we'd get, cross out the joules, and we get 45 kilojoules over 1,000 kelvins.
Okay, is that your final answer?
And that would be 9 kilojoules over 200 kelvins, which is basically 0.045 kilojoules over kelvins.
So what was your final answer?
0.045 kilojoules over kelvins.
Good. So for simplicity, you can do this all in one step at this point. So notice that if you cancel the joules now, you get the units that you get your target units, which are kilojoules per Kelvin. If you cancel the joules, you get your target units, which are kilojoules per Kelvin. So now you can just do the calculation. Remember, you can ignore the ones, so the calculation is just 45 divided by 1,000. So you can just do the calculation 45 divided by 1,000 in one step, and that'll give you this answer. So this is a case where we started with a fractional unit and we ended with a fractional unit. This is a case where our target units are fractional and our starting information is also fractional. So we started with a fraction and we ended with a fraction. Okay, let's do this version of the question. How would you attack this?
So our target unit is the change of entropy, which units are J over K.
That's a good start.
We can use the equation, the change of S system equals the change of H reaction over T. And then we would have to convert 163.2 kilojoules into joules. So that would be 163.2 kilojoules times 1000 joules over 1 kilojoule. And that gives us 163,200 joules. And then the temperature we need to convert from Celsius to Kelvins. So we'd have to do 25 plus 273.15, 15. So that would give us 298.15 kelvins. And we can simplify that to the change of S equals 550 joules over Kelvin.
What was your result again?
550 joules over Kelvin.
Okay. Did this result come out to be positive or negative?
Positive.
So I'm going to report that as positive. Since delta S could be positive or negative in theory, it's actually a good idea to put a positive sign in front of positive results. So I'll say that this is positive. Okay, that seems like a good approach. That was a good approach for this question. That was a good use of this equation. Remember, you won't find this exact equation on the formula sheet, so it's a good idea to actually memorize this equation. So you said the question was asking us for delta S. To be more specific here, it might be a little bit better to say it's the delta S for the system, because there are other delta S's that they could ask you about. So we'll write down that they're asking for the delta S for the system in this case. Okay, it's good that you saw that you had to do a lot of unit conversion for this question. There's a unit conversion from kilojoules to joules. There was also another unit conversion from Celsius to kelvins. So it's good that you identified both of those unit conversions. In general, whenever a chemistry formula refers to the level of the temperature must be written in kelvins before it's substituted into the formula. This problem told us the level of the temperature in degrees Celsius, so this temperature must be converted into kelvins before it is substituted into this formula. Here is the general formula for converting the level of the temperature in degrees Celsius into the level of the temperature in kelvins. You can see that we can use this equation for this problem. We use this equation to see that 25 degrees Celsius is equivalent to 298.15 kelvins. So this is the number that we plugged in to this formula. When a formula refers to the level of the temperature must be written in kelvins before it is substituted into the formula. Okay. All right, well, I think you can practice some more of those in the homework, but I think you're getting the basic idea. Whoops, so let's move on. So let's see if we can find any other useful equations in the formula sheet for the concepts that we've been talking about here. Okay, so let's see. What would you say this symbol stands for?
The change of entropy in the reaction.
Good. Now, we haven't talked about this little circle before. What does the little circle mean? That little circle means standard conditions. When you see the little circle, it means standard conditions. What are standard conditions? Standard conditions are considered to be a pressure of 1 atmosphere and room temperature. Room temperature, those really are standard conditions in the lab, right? In the lab, you usually will be at 1 atmosphere and room temperature. Remember that room temperature is 25 degrees Celsius. For the sake of completeness, I will also mention that standard conditions also requires the concentrations of all starting materials and products to be equal to 1 molar. For most of the problems that we'll be working on in this video series, these details will not be very important for solving the problems. So when you see the little circle, that means standard conditions, 1 atmosphere and 25 degrees Celsius. So this would be the change in entropy of the reaction under standard conditions. The change in entropy of the reaction under standard conditions. That could also just be called the standard change in entropy of the reaction. Okay, now this symbol stands for the standard level of entropy of the products. This is the standard level of entropy of the products. And this would be the standard level of entropy of the reactants. What do the N and the M stand for? The N and the M stand for stoichiometric coefficients. N and M represent stoichiometric coefficients. Remember here we're talking about a reaction. We're talking about a reaction, so the reaction will have stoichiometric coefficients. So N stands for the stoichiometric coefficients on the products, and M stands for the stoichiometric coefficients on the reactants. Do you know what this symbol means?
The summation.
That's right, so it basically means add. But notice that here there's a negative sign. So really what this means is that we are subtracting the entropy from each reactant. What we're really doing here is subtracting the entropy from each reactant. We're not really adding them. Because of this negative sign, we're really subtracting. So we are adding the entropy of each product, and we're subtracting the entropy from each reactant. What would be the units for this concept?
Joules over Kelvin.
That's right. Oh, now I have to actually warn you of something that I forgot to mention earlier. Remember we said that the units for entropy are joules per Kelvin. But actually that was an oversimplification. Actually, there's actually going to be some inconsistency here. Sometimes we're going to be using joules per Kelvin. Sometimes we're going to be using joules per Kelvin per mole in different contexts. So we're going to be somewhat inconsistent in our units for entropy. Sometimes we'll be using joules per Kelvin. Sometimes we'll be using joules per Kelvin per mole. So hopefully it will be clear from the context in each case which are the appropriate units to use for entropy, joules per Kelvin or joules per Kelvin per mole. If you're figuring out the entropy from this equation, you would get joules per Kelvin. Now, where are you going to get these numbers from? Where will you find the entropies of the products, and where will you find the entropies of the reactants? Well, actually, those are going to come from a table. So let's look at the table. But then this next page is standard thermodynamic quantities. So let's take a look at this table here. So notice there's a whole bunch of different substances in the table. And then looking in the table, what does this symbol stand for?
The change of enthalpy.
That's right, this is an enthalpy change. This is a concept that you and I haven't talked about yet, but you might remember it from class. And what does this symbol stand for?
That stands for standard conditions.
Good. What's the whole symbol stand for? What's the S stand for?
The S stands for entropy.
Okay, so this symbol would be the entropy under standard conditions. So this column is the entropies. Notice the units they're using. Here they're using those units I warned you about. Instead of using joules per Kelvin, they're actually using joules per mole per Kelvin. So these would be the entropy changes. So the point I'm making here is, where do you find the entropies for the right-hand side of this formula? The entropies for the right-hand side of this formula come from this table. So let's add that to our notes. These entropies and these entropies will be taken from the table. Now this table is a little difficult to use because notice this is a huge table. Here's page 1. Here's page 2. Page 3. Page 4. Wow, it's longer than I thought. Page 5. Page 6. It's a 6-page table. Now notice that it's organized alphabetically. Here we have aluminum substances, here we have barium substances, beryllium, bismuth, boron. All right, but notice that sometimes you might have a little difficulty finding something because after all, molecules have more than one thing in them. So for example, where would you look for this substance? You might start by looking for it in the chlorine section, but notice it's not in the chlorine section, it's in the boron section. So you might have to look at a substance in more than one place before you can find it. Here's bromine, cadmium, calcium. Notice here, FeO. So notice, where would you look for the FeO? Well, you might start looking for the FeO under oxygen, but you wouldn't find it there, you would find it under iron. So my point is, if you don't find the substance in the first place that you look, then check for a different element, because every substance has more than one element. Logically, this could have been under iron or under oxygen, but it turned out that it's under iron. Did you notice these are in alphabetical order? So here we have the B's, then the C's. So they're in alphabetical order. Okay, like I said, I forgot to warn you about something else. You need to be very careful when you use this table because some of the entries are very similar. So you have to be careful to pick the correct entry. So for example, notice here, suppose you're looking for boron. There are separate entries for boron solid and boron gas. So you have to be careful. Don't just pay attention to the element, pay attention to the phase. If you're looking for boron solid, you don't want to accidentally pick a number for boron gas. Or if you're looking for boron gas, you have to be careful not to accidentally pick the boron solid. So pay careful attention to both the element and the phase when you're working in this table. Notice here, here's Br2 liquid, here's Br2 gas. Notice how it would be very easy to get these confused. This is neutral Br, gas, Br2, liquid, Br2, gas, and here's Br minus aqueous. So look at the entire entry to make sure that you're getting all the parts of the entry correct. It would be easy to pick the wrong row here. So take your time when you're using the table to make sure that you're picking the correct row in the table. Here's another example, CCl4 gas versus CCl4 liquid. You can find a link to this table in the video description box. You should also be able to find a version of this table in your textbook, but be aware that the precise numerical values in your textbook might differ somewhat from the numerical values in this table that we used during the tutoring session. Okay, let's try this question. I think we'll go through this problem together. So you want to start by identifying the question. So what would be a good symbol for what this question is asking us?
It's asking us for the standard change in entropy.
Good. What would be a good symbol for the question?
Delta S or delta S and the little I forgot what it's called, like the thing you usually put for like temperature.
Okay, maybe you mean the little circle?
Yeah.
All right, and so it's cool with me if you just call it the little circle, but you can say also, you could say it stands for standard conditions. So it's the standard condition symbol, it's the little circle. Also, we can notice this is asking for the entropy change for this reaction. So we could call, to give it a full symbol, we could write it out like this. Okay, so notice here that they actually gave us a reaction. They actually gave us a reaction, so we can use this formula. We can use this formula to solve the problem. Delta S for the reaction equals sum of the entropies for the products minus sum of the entropies for the reactants. So let's go through that here. So notice that we start here with the products. We start with the products. So our product here is water liquid. Water liquid. Now remember, N stands for the stoichiometric coefficient. So this stoichiometric coefficient is a 2. Now remember, this number comes from the table. So can you find water liquid in the table? You have that table with you. See if you can find water liquid in the table.
I don't know. I can find it.
Okay, I know it's a long table, so let me give you some help. Where are you looking? Are you looking under hydrogen or are you looking under oxygen?
Under hydrogen?
Okay, and did you find it there?
No.
Okay, so where should you look next?
Oxygen?
That's right. So let's see, can you find it under oxygen?
Yes.
Okay, all right. So what number do we write down?
70?
So this would be 2 times 70. I can see why you would look under hydrogen first, because the hydrogen comes first in the formula. But notice it's actually under oxygen. It's actually under oxygen. Notice you have to be careful here. Do we want water liquid or do we want water gas?
Liquid.
Because that's what's in the formula. That's what's in the equation. In the equation, they wanted water liquid. So be careful to pick the correct row. Notice that if you were in a hurry, you could easily pick the wrong rows here. Here's H2O2. So try to be careful to pick the correct row. Okay, now let's move on to, that's the only product, so now we move on to the reactants. Now to simplify things, remember that we can really just treat these as subtracting the terms for the reactants. If you're adding a sum, that's the same as subtracting. So let's subtract the term for the H2. So notice that the H2 has a stoichiometric coefficient of 2. And now we need to get the number for the H2. So can you find the number for the H2 in your table?
It would be 130.7.
Good. Notice that you're looking for H2 gas. You're looking for H2 gas in the table, 130.7. Good. Make sure you're picking the correct row. What would you do now?
We would have to put. Oh, we would have to add oxygen.
Good.
O2.
Now, but remember, because of this minus sign, we're actually really subtracting the term for each reactant rather than adding it. If you subtract an addition, that's the same as a subtraction. So to save time, you can just say that you're subtracting the term for the oxygen. What's the stoichiometric coefficient? What's the stoichiometric coefficient for the oxygen? Remember that this stands for the stoichiometric coefficient. So what's the stoichiometric coefficient for the oxygen?
1.
Good. All right. And then what would be the entropy for the oxygen?
It would be 205.2.
Okay, good. Now, of course, you know that multiplying by 1 doesn't change the value. Multiplying by 1 doesn't change the value, so if you like, you could just leave the 1 out. If you like, you can just leave the 1 out and write it like this. It's up to you. Now we can do the calculation. So let's do the calculation and see what we get.
I got negative 326.6.
And the units for that would be joules per Kelvin. Okay, good. So are we ready to answer the question?
Yes.
Okay, and what would the answer be?
The change of entropy standard conditions in the reaction is negative 326.6 joules over Kelvin.
Good. So here's the method for solving this type of question. Don't forget to put in the stoichiometric coefficients. Remember that we're adding the entries for the products, but we're subtracting the entries for the reactants. Remember again to take your time in the table to make sure that you're getting the exact right row in the table. The mathematics for using this formula might make more sense to you if you write down a step that looks like this, using brackets. This symbol is referred to as the sigma symbol. The sigma symbol means sum, and the word sum means addition. So, this sigma symbol tells you to add all the terms for the products. Therefore, inside these brackets, we add all the terms for the products. Now, in this particular chemical reaction, it turns out that there is only one product. So we only have one term to write inside these brackets. Then, this sigma symbol tells you to add all the terms for the reactants. So inside these brackets, we add all the terms for the reactants. Next, in this line, we can simply drop the brackets around the sum for the products. However, because of this subtraction symbol, mathematically we cannot simply drop these brackets around the sum for the reactants. Instead, we need to distribute this subtraction symbol over each term for the reactants. During the tutoring session, I guess I was encouraging the student to do this step in her head and to begin by writing this step on paper. But that might not have been the best advice for all students. You might be better off if you begin by writing this step on paper, and then proceed to write down this step where you drop the brackets around the sum for the products, and you have to be careful to distribute the subtraction sign over each term for the reactants. Now, let's make sure you understand where these numbers came from. These numbers are taken from the table. This number 70 refers to the standard entropy level for the H2O liquid product. Here's where we got that number 70 from the table. We're looking in the third column of the table. The third column refers to standard entropy levels, and we're looking at this row for liquid water. Make sure that you don't look at the row for gaseous water or for H2O2 liquid. Notice that it turns out that we don't find the H2O under hydrogen. Instead, we find the H2O under oxygen. By the way, notice that the units for this number are joules per mole per Kelvin. This number, 130.7, refers to the standard entropy level for the H2 gas. Here's where we find the 130.7 joules per mole per Kelvin for the H2 gas. Make sure that you're looking at the correct row again. We don't want the row which has H gas. We want H2 gas. Notice that this number is found in the section for hydrogen. Remember again that this table lists the elements in alphabetical order. This number, 205.2, refers to the standard entropy level for the O2 gas reactant. Here's the 205.2 joules per mole per Kelvin for the O2 gas. Notice that that's found in the oxygen section. Make sure that you pick the correct column and the correct row. We want the third column, which has the standard entropy levels, and we want this row for O2 gas. We don't want the row for O gas or for O3 gas. Also, let's make sure that you understand what the N and M stand for in this formula. Remember that in this formula, the N and the M stand for the stoichiometric coefficients. And I hope you know that these numbers from the chemical reaction are the stoichiometric coefficients. So this 2 represents the stoichiometric coefficient for the H2O liquid product. And this 2 represents the stoichiometric coefficient for the H2 gas reactant. And you should know that if a particular stoichiometric coefficient is not explicitly written in the chemical reaction, that means that the stoichiometric coefficient is a 1. So, this 1 represents the stoichiometric coefficient for the O2 gas reactant. Now, let me also warn you about something that often causes students to make mistakes when they're using this formula. Notice that in this formula, the products are written on the left, while the reactants are written on the right. Now, that often causes students to make mistakes because in the chemical reaction, the reactants are written on the left, and the products are written on the right. So, remember, when you're using this formula, be careful to write the products on the left of the formula, even though the products are on the right in the chemical reaction, and be careful to write the reactants on the right in the formula, even though the reactants are on the left in the chemical reaction. Now let me point something out. Do you see how this question was solved differently from this question? So how did we know to use two different formulas? Well, notice that in this formula, they asked you for in this problem, they asked you for the entropy change, and they gave you the delta H. Here they asked for the entropy change, and they gave you the delta H. Well, if they give you the delta H and ask for the entropy change, that's a clue that you should use this formula, because this formula relates the delta H and the entropy change. But notice that in this case, they just asked us for the entropy change, and they didn't give us any delta H's. They just gave us the reaction. So in this case, that was a clue that the best approach was to use this formula, just based on the entropy levels from the table. So my point is that there's different types of problems that you solve using different formulas, depending on the information that you're given in the problem. Okay, let's try this question. How would you attack this?
So we write the equation delta as to the standard conditions in the reaction equals the sum of n as little circle product minus the sum of m as little circle reactants.
Okay.
So then we do 2 I have 2 times 188.8 plus 2 times 248.2.
That's right, plus. Okay. Okay, so let's continue.
Then we can subtract 2 times 205.8 plus 3 times 205.2. Would you put parentheses around each product? Parentheses like around 2 times 188.8 plus 2 times 248.2 and then close parentheses, and then do the same for the reactants.
So like this?
Yes.
Okay, that you certainly could do that. You certainly could do that. That is mathematically correct. That is mathematically correct. But maybe we can simplify this a little. Can we simplify this? So now that you put these brackets in, can you drop these brackets?
Yes.
Yeah, so maybe it's better not to put them in the first place. Now, what about these? You can't just drop these, you would have to distribute the negative sign. But my suggestion to you is that it would be easier just to subtract from the beginning rather than putting in brackets. This is what I was mentioning to you earlier. Subtracting a sum is just the same as subtracting. So rather than, I mean, you can do it whatever way you want. You can do it however you want. But I think it's easier just to add each term for the products and subtract each term for the reactants. That way, otherwise we're cluttering things up with a bunch of brackets. So what you said was mathematically correct. What you said was mathematically correct, but it might be simpler just to write it like this. Just add each term for the products and subtract each term for the reactants, because that's what you would end up with anyway. If you put in these brackets, if you put in the brackets like this, well then the next step would just be to distribute the negative sign over the two terms, and you would end up subtracting each term anyway. Okay, you don't have to do it this way, but I think this will give us less clutter. Okay, so let's continue.
And that would give us negative 153.2 joules over Kelvin, which is choice A.
Here is the complete math for using this formula. In the first line, we put brackets around the sum for the products, and we put brackets around the sum for the reactants. Then we can simply drop these brackets around the sum of the products. We cannot simply drop these brackets. Instead, we need to distribute this negative sign. over each term for the reactants. During the tutoring session, I was encouraging the student to do this step in her head and to begin by simply writing down this step. But that might not be the best advice for all students. You might be better off if you do write down this step with the brackets first, and then write down this step without the brackets, but being careful to distribute the negative sign over each term for the reactants. Now, here's something that you might have been wondering about. You might have noticed that the units for each of these entropy levels is joules per mole per Kelvin. Those numbers come from this table, and you can see that the units for this column in this table are joules per mole per Kelvin. Well, if the units for each of these entropy levels is joules per mole per Kelvin, you might have been wondering how come our final result came out in units of just joules per Kelvin. What happened to the per moles? Well, here's the answer to that. What are the units for these stoichiometric coefficients? What are the units for n and m are stoichiometric coefficients? Well, in this context, we assign units of moles to each of the stoichiometric coefficients, and now you should be able to see that the moles will cancel. The units of moles will cancel. And now you can see that the correct units for our final result when we use this formula really are joules per Kelvin, which matches the units in the choices. Okay, good. Good. All right, remember again, there's two different types of entropy problems. Another type of entropy problem is when we use this equation. But we didn't use this equation for this problem because they didn't mention enthalpy. They only mentioned entropy. Let's be systematic here and write down a symbol for what the question was asking us. What would be a good symbol for what this last question was asking us?
The question was asking us to, for the change of entropy, and then the little circle and the reaction.
So delta S circle reaction. So it's a good idea to start with the symbol for what the question is asking. All right, maybe we'll try to mention one more topic before we finish today. So what does this symbol mean? Well, can you remind me, what does this part mean?
The change of enthalpy.
Good. Now, do you know what the F means? This stands for formation. So this is called enthalpy change of formation. Enthalpy change of formation. Enthalpy change of formation, delta HF. What does that mean? The enthalpy change of formation for a compound, say Y, is the enthalpy change for the reaction that produces compound Y out of elements which all begin in their standard states. Enthalpy change of formation for compound Y is the delta H for the reaction that produces compound Y out of starting materials which are elements in their standard states. What's a standard state? The standard state of an element is the ordinary form in which the element is ordinarily encountered. I'm not going to go into too much detail about this definition because actually I don't think you need to understand this definition in too much detail for the test. For the test, I think you mainly just need to focus on the formula for delta HF. So let's look at the formula sheet and see if we can find a formula for delta HF. So here's the formula. So let's review this formula. What do you think this symbol stands for?
Delta, the change of enthalpy in a change of enthalpy in standard condition of a reaction.
Great. And what does this stand for?
The change of enthalpy of formation in standard conditions.
For each product. This is the enthalpy, standard enthalpy change of formation for each product. Good. So what would this stand for?
The change of enthalpy of formation in reactants.
For each reactant. Good. What do you think the N and the M stand for?
It stands for the stoichiometric coefficients.
That's right. You can see this equation is quite similar to the equation we looked at previously. So these are stoichiometric coefficients. Okay, let's see. Where were we? So where will you get these numbers from? Where do these numbers come from? Those numbers come from the table. Can we find those in that? Here's that same table we were just looking at. So take a look at the first column. What do the numbers stand for in the first column?
That stands for the change of enthalpy in formation.
That's right. These are the standard enthalpy changes of formation. So notice that the first column is for standard enthalpy changes of formation. The third column is for standard entropies. So we don't want to confuse those with each other. So this table has both entropies and enthalpies of formation. So we can find those all in the table. Okay, what would be the units for this concept?
Joules over Kelvin.
I think that you got confused there. That's for entropy.
It's capital H.
That's the symbol. So what would be the units?
Joules.
Joules or kilojoules. This could be measured in joules or kilojoules. In this context, it would usually be kilojoules. Let me warn you about something else about enthalpy, similar to what I told you about entropy earlier. I said earlier that enthalpy is in joules or kilojoules, but I should have warned you that it could also be in joules per mole or kilojoules per mole. Again, there's going to be a little inconsistency. We'll be a little inconsistent in our units. Sometimes we'll use kilojoules for enthalpy, and sometimes we'll use kilojoules per mole. You'll have to look at the context to see what the appropriate units are. Okay, I think this will be our last question for today. So how would you attack this problem?
The target units are the change of enthalpy standard conditions, and you can use the formula delta H little circle reaction equals summation N delta H little circle formation products minus the sum of M times delta H little circle formation reactants. And then we can do 3 times negative 187.8 minus 3 times 0, which is just 0, minus, plus, well, yeah. Oh, actually minus 0 as well. So it'd just be 3 times negative 187.8, which gives us,
Where did this come from?
oh, sorry, negative 241.8.
Negative 241.8.
And that gives us,
Well, hold up. Sorry. Let me, sorry to slow you down. Where did this number come from?
oh, I was looking at the gas, sorry, 285.8.
Okay.
Negative.
285.8. Remember when I was warning you, it's easy to pick the wrong number from the table. So this is what I was talking about. It's very easy to pick the wrong number from this table. So you really have to take your time and double check to make sure that you're picking the correct number from the table. Okay, so now I think this number is correct. So now let's keep going. Where did this number come from?
Well, that came from H2 gas, which
Okay,
is,
good. And where did this number come from?
oh, that's O, oh, O3 gas, that's 142, so 142.7.
Okay, so again, that's why I was warning you earlier. It is very easy to accidentally pick the wrong number from this table. You have to look at be very careful to look at the exact details to make sure you're getting the exact right number from the table. All right, hopefully we've got the right numbers now, so let's try this again.
I don't think it's 3 times.
Oh, did I get confused? Oh, yeah. Thank you. So, yeah, so how would you write this?
Minus 142.7.
That's right, because we're multiplying by a 1. So that was my mistake. I was making a mistake there. Thank you.
When simplifying, I got negative 1,000, which is option D.
All right, let me get caught up with you there. Okay, what would be the units on this result?
Joules, but wait, oh, sorry, kilojoules over mole.
They told us what the units would be. They told us the units would be kilojoules per mole. And that's consistent with the table, because if you look at the table, the entries from delta H in the table are in kilojoules per mole. Actually, on second thought, I think that this problem is slightly miswritten. And it would be better if the problem said that the choices are in units of kilojoules rather than kilojoules per mole. These numbers from the table are in units of kilojoules per mole. You can see that this number from the table is in units of kilojoules per mole. But as I mentioned earlier in this video, N and M, the stoichiometric coefficients, have units of moles. So we can see that the units of moles cancel, and therefore the final correct units for our result when we use this formula are kilojoules. So as I said, this problem does appear to be slightly miswritten. The problem probably should have said that the units for the choices are kilojoules rather than kilojoules per mole. This type of error or inconsistency about the correct units is probably not that uncommon in exam problems that deal with this formula. All right, so you said we're going to end up picking choice D. All right, that looks good. Okay, so notice here that we were having a lot of trouble with picking the wrong row in the table. So you have to be very careful here. Pay close attention to whether you're looking at a gas or a liquid, and pay close attention to the subscripts. Here we're not looking for O2, we're looking for O3. So you need to be really take your time and get the correct number from the table. Be careful to get the correct numbers. from the table. The chemical reaction deals with liquid water. So here's the value that we need to take from the table for liquid water. Make sure that you're taking a value from this column, the column for the delta H of formation, rather than, say, this column, the column for entropies. Make sure that you're picking the correct row. For example, don't pick this number because this number is for water gas rather than water liquid. And don't pick, say, this number because this number is for H2O2 liquid. But what we want is H2O liquid. We also need a number for H2 gas. So we take the number 0 for H2 gas. Make sure that you're taking the number for H2 gas rather than the number for H gas. Now, notice that it turned out that the standard heat of formation for H2 gas is 0. And it turns out that that's no coincidence. In fact, we could have predicted, even without looking at the table, that the standard heat of formation for H2 gas would be 0. I will explain how we could have predicted that this heat of formation is 0 in the next video in this series. And we also need the number for O3 gas. And we take the number 142.7 for O3 gas. Make sure that you do not accidentally take the number for O2 gas. This problem is dealing with O3 gas. Let me warn you about something else here. In this formula, who comes first in the formula? Products or reactants?
The products.
But notice that that could be confusing because in the chemical reaction, the products come second. So I just want to warn you about that. Notice that even though products are second in the reaction, we write them first in the formula. And even though the reactants come first in the reaction, they come second in the formula. So if you get confused about that, you'll put the minus in the wrong place. So you have to be careful here. Like you said, we put a minus in front of every term for the reactants. We put a minus in front of every term for the reactants. That's the technique we've been using here. If that's too confusing for you, you could just do it like this. You could put extra brackets around it, but for me it's simpler to put a minus in front of every term for the reactants. Here is the complete math for using this formula. In this line, we write brackets around the sum for the products, and we write brackets around the sum of the terms for the reactants. Then in the next line, we can simply drop the brackets around the sum for the products. However, we don't just drop the brackets around the sum for the reactants. Instead, we need to remember to distribute this negative sign over each term for the reactants. In the tutoring session, I encourage the student to do this step in her head and to begin by writing down this step on the paper. But in reality, you might be better off if you do write down this step on paper. I offer academic tutoring in general chemistry and other subjects. For more information, go to my website. There's a link to my website in the video description box.